Welcome to the Jack Westin MCAT Podcast with your hosts, Michael Maleka
and Molly Kilty. Hello, everyone, and welcome back to another episode of our Jack Westin MCAT Podcast with your hosts, Mike and Molly. Mike, I'm really excited for this episode, as always, but I think particularly for this one because we get to talk about the basics, the sort of preliminary information to one of the most important senses that we have as human beings, very visual creatures. We're going to talk about light.
And optics.
And optics. Yeah, I was getting there.
100%. I was like, light and we finished each other's sentences. That's just great.
Yeah.
But yeah, because I think this is a great callback to kind of what we did kind of the last few episodes where we started on the brain, the vital functions of the brain. You know, we talked about the movement, the parts of the brain involved movement. Then we went to waves, right? To talk about waves because we were going to be talking about the hearing, like about our hearing pathways, because we need to know about waves in order to understand how we hear. We're kind of doing the same thing here, but instead of just general waves, we're diving deep into one of the most important waves, not only on the MCAT, but also just in nature, which is light. Because we'll be steering back once we kind of cover this physics topic. What we need to know, we'll be steering back to the biological system that the MCAT loves to test, which is the occipital system. Kind of hint, hint, nudge, nudge. But we are starting with the eyes and not the eyes, light and optics, which is so important because especially physics loves to test this concept.
Yes, and I honestly I love talking about vision and the physics behind vision because again, we are incredibly visual creatures, right? Like we base so much of what we understand about our environment on visual information. And it's fascinating to think about how that light wave ultimately reaches our eye from sources as far away as like literal, the sun, like light years away, even if we're thinking about other stars that we see in the sky, right? Like how does this work? How does that light source how is it going to enter our eye, literally enter, and how, in our next episode, does that information get encoded into a neural impulse that gets sent to the brain for perception? So I'm very excited about this, especially because of how many ways that our eyes get tricked by things. It's important to start with the basics. So if you're thinking about light, right? And again, we talked a little bit about it. It's important to just kind of recap the basics of light as a wave. Mike, give us the basic need to know that we've talked about already.
Fantastic. This is kind of what we talked about when we talked about waves about 2 episodes ago. One, it's a transverse wave. So that means it travels perpendicular. The direction that the particle is moving is perpendicular to the actual direction of movement as opposed to a longitudinal wave, which is like parallel in the same direction. So, if it's moving left and right, therefore the particle is moving up and down. That's kind of the disturbance is up and down. So it's a transverse wave. But light is a very special wave. It's a very cool wave because unlike something like sound, it does not need a medium to travel, right? It is in itself a particle, a photon, so it can travel without a medium. It can travel in the vacuum of space. That's why we can see things millions and millions of light years away because, hey, there's nothing in between, but it didn't need anything in between. It can travel without a medium. Right, just like a wave, it has an amplitude, right? While the photon itself doesn't have an amplitude, it's more like the bundle of photons together is the amplitude. But like all waves, there's a frequency, right? There's a speed of the wave, there's the wavelength, right? And so it still follows the speed of a wave equation, v equals f lambda. However, because light is so important, it is very important to know the speed of a wave in a vacuum, because like all waves, the speed of a wave is determined by the medium it travels in. Doesn't matter the frequency, doesn't matter the wavelength, it's always determined by the medium. So we talk about the speed of a wave in a vacuum is 3 times 10 to the 8 meters per second. Again, that's incredibly fast. And until very recently, we believe that's the fastest you could ever travel. That's like the universal speed limit. Right? Like nothing in the universe can travel faster than light until very recently. There were particles discovered that do. But that's so beyond the scope of the MCAT that it's unbelievable. But like it is the fastest thing you're ever going to see is going to be the speed of light, which is like what is it? 3 times 78 is like 300 million. No, I'm missing some. Yeah, 300 million. Yeah, a lot of zeros there.
Approximately a lot. It's approximately very
Approximately,
fast.
approximately a lot of speed. So light travels very, very quickly, but it won't always travel that speed. It will depend on the medium, which might be relevant for one of the conversations we have today. So I don't think I missed anything. That's kind of like a good like recap. If you want like a deeper dive, you're like, whoa, Mike, you went way too fast about light. Go check out our waves episode where we kind of like really walk through like the properties of a wave.
Yes. You went faster than the speed of light. Just
Ah,
kidding.
just kidding. That's impossible.
Just kidding. That's actually, and the speed of sound is much, 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 much lower than the speed of light.
Right.
About 343 meters per second. Very different from
Mhm.
3 times 10 to the eighth meters per second. Anyways, that's sound. But yes, that was a perfect recap of light. I don't think you missed anything from what we had talked about previously. We want to build on that today, right? Because we understand light as a wave, but
Mhm.
how can we impact light with different optical instruments, right? And
Mhm.
how does light change when it changes media, for example,
Mhm.
right? And I feel like when we talk about how light behaves, right, kind of an odd phrase or an odd word to use, but it's fair, right? The behavior of light, there are a couple different ways that we can see things happen. Okay, so one
Mhm.
of the most commonplace, right, ways that we interact with light is actually something you probably used already, right? Today, when you're, combing your hair, brushing your teeth, right? It's a mirror, right? There's an idea that light can be reflected off a surface. And it's
Mhm.
not just mirrors, it's all around you, right? If you're staring into a still lake or pond, you're looking down and you're seeing your reflection, right? I think we're all pretty comfortable with the idea of reflection. Light
Mhm.
bounces off something, comes back. There's also an idea of refraction, and this is going to be really, really fun to describe and
Mhm.
also very important for our discussion of vision and of light in general, right? Which is if you are going from one medium to another, the
Mhm.
light may seem like it bends. It doesn't
Mhm.
actually bend, but as you've stated very clearly, the speed of a wave depends on the medium. If you change medium, you're going to change speed, and that might change the behavior of that wave. Um, and we can get into kind of a fun, like almost overlap of these concepts when we talk about total internal reflection too. Um,
Mhm.
this one's really interesting. There's a lot that we can discuss, especially as someone who loves snorkeling and diving and things like that. A couple really cool applications, but we're going to get in, especially in this podcast, reflection and refraction. And of course, as part of that, we're going to talk about mirrors. We're going to talk about lenses. We're going to talk about converging and diverging systems. We're going to talk about images and objects and, all of these fun things. So
Right.
I'm very excited.
Right, right. And like you said, like I think a perfect place to start is the behavior. Let's talk into that behavior, like you said, that we've likely all experienced. Like I know this morning I experienced this behavior because I looked at a mirror, right? And that
Yep.
light reflected. But let's talk about what's going on. Because while we all experience reflection on like a day-to-day basis, let's get into the specifics of what's happening when you see yourself in the mirror. Because what's going on is the light is reflecting off the surface. So the light originated from you, right? When you looked at a mirror, the light originated from you. The light, I mean, maybe like the light above you from your lamp or your kind of I don't know why, spotlights in your bathroom shone off you, like off your skin, and then came off you, right? It came off your skin, came off my maybe my
You're
beard.
glowing.
Yeah, because I'm
You're glowing,
glowing in the
Mike.
morning. Absolutely, totally don't need like yeah, me in the morning without caffeine, very not glowing. I'm gonna be honest. But it's gonna be bouncing off, it's gonna be coming off me and hitting my mirror. And now, we like you said, there's kind of two behaviors that we can have, reflection and refraction. However, in this case, we are seeing reflection where it's not going through the mirror, it's bouncing off the mirror. It's bouncing off the mirror, and when you're experiencing it, it's bouncing off the mirror and entering your eye, right? And that's why you can see yourself. It's because the light that came off you hit the mirror and came back and entered your eye. Now, this is where we can start talking about a few of the rules of how that bouncing can occur, right? The main rule is the law of reflection. And this idea is the angle of incidence, which is kind of a fancy term for the light that actually hits the mirror. The way that will reflect will always be equal to that original angle. So the idea is the angle of incidence equals the reflected angle. If my light hits the mirror at 30 degrees, it will be reflected at 30 degrees. But let's be very, very careful here because when you see images of this, right, it might hit a surface at a certain angle, but if it's hitting at an angle, there's kind of two options for which angle you'll take. There's either the angle between the light ray and the surface, or the angle between the light ray and what we call the normal, right, which is this line perpendicular to the surface. When we talk about reflection and refraction, whenever we're talking about an angle, it is always, always, always the angle between the ray and the normal. Always the angle between the ray and the normal, right? It's kind of hard to visual. It's always with the podcast. It's kind of hard because I'm like always usually used to teaching this with like a picture, but maybe we can bring up a picture, possibly editors, of like what I mean by that normal. It's always that angle. Very, very common MCAT mistake is to think, oh, it's the angle between the ray and the actual surface itself. So it's
Yeah.
kind of that angle there.
Yeah. I feel like it's helpful to visualize, right? Because we're talking about light, but
Mhm.
also we can talk about analogies for reflection all over the place, right? If you
Mhm.
ever played billiards or
Yeah, yeah.
pool, that's basically what you're doing, right? It's a
Mhm.
little more complicated because you're hitting the one ball into another, which then moves off. But if you just
Mhm.
were to smack a particular ball with your
Mhm. Mhm.
pool cue, it's going to go and it's going to bounce off at a particular angle, the wall, and it's going to continue, right, in a different
Mhm.
direction. If you were thinking about the actual rectangular pool table, right, and the wall or the border of that pool table is that's the surface, right? The normal would be on like laying on the pool table, right? But
Mhm.
going to the other wall, right? It's perpendicular to that surface. And
Mhm.
you can imagine, right? Like if you are hitting the ball against it, you can almost see the angle. And if you've ever
Mhm.
played billiards, that's what you're trying to visualize when you're trying
Mhm.
to line up a shot in a particular way, right? Or you could even just think of like a ball bouncing on the ground, right? Like the ground is the surface. The perpendicular, right, or the normal line would be sticking up off the ground,
Mhm.
right? Completely vertical. And you can imagine, right? Like it's easier sometimes when you think beyond light, which is in many cases very abstract, despite it being present all around us. Think about an actual a ball or a material that bounces off something because it's
Mhm.
essentially the same. It's the same principle on a deeper level.
Mhm.
So that angle will remain the same. And
Mhm.
again, we're talking about light, so we're talking mirrors, we're talking about, the surface of water, of a lake, right? There's lots of ways that you could see your reflection. Maybe you're staring at, a very shiny doorknob. Who knows?
Love
But it's
that
the
doorknob.
same, it's the same general principles. Um, so, and if this got disturbed somehow, let's say you're sitting, on a boat or on a dock, you're looking over at the surface of the water, it's perfectly flat. If you threw a rock in the water, it's not gonna, those light rays, yeah, are still bouncing off the water. They could still reflect, but because the surface is so uneven, you're not gonna see it, right? There's lots of ways that you could apply this, and what would happen if something was disturbed. But I think the key thing here, light is bouncing off a medium, and the angle from the actual surface in that perpendicular normal line will remain the same, incident
Mhm.
and reflected.
Mhm. Mhm.
That's the most important stuff about
That's
reflection.
the angle of incident angle reflection, very, very, very testable. And again, a great reminder though, that light, it's not entering a new medium when it gets
Yes.
reflected. So therefore, if it's not entering a new medium, Molly, is the velocity of that light going to change?
Nope.
Absolutely not. Because you might think, oh, maybe it lost energy. Maybe it was a perfect reflector. Oh, does the speed change? Absolutely not. If the medium does not change, the velocity doesn't change. The velocity will stay the same. We can talk about
Yeah.
like imperfect reflectors, but again, an imperfect reflector is something that, maybe some of that energy is lost after reflection. Well, that
Yeah.
might impact other aspects of our wave, but not our velocity. Our velocity will
Yes.
stay the same.
Yeah.
Mhm, mhm. And so now that we understand reflection, right? I think that reflection is usually the easier one to understand. Angle of incidence, angle of reflection, pretty easy. Now we can take this one step further because we brought in a great example where, okay, let's say you're looking down at the water, right? You can see yourself, but when you look at the kind of reflection of yourself on the water, it's not a perfect image. It's not like as if you were looking at a mirror. It's not as clear because not all the light is getting reflected back at you. Well, you might be thinking, well, if not all the light's getting reflected back at you, well, where is that light going? right? It must be going through and into the water. And when we're going from when light particularly goes from one medium to another medium, changing mediums, this is what we call refraction, right? We're not just staying in the same medium, we're going to a new medium. But again, big idea that I want you to remember. If we are going into a new medium, what must change?
Velocity.
Has to change, has to change. The speed must change. And a result of this speed change is the trajectory will also change of this light. So talk to me about that, Molly. What's going on here?
I love talking about refraction. I think it's
Mhm,
so fascinating. I
mhm,
think it's been something I've been curious about ever since I was a kid. And I would
mhm,
look, I mean, I always was, I grew up around the ocean, was always in the water. And it was always so confusing. Like when I would look down and I would see like a really pretty shell or something, I'm like, oh, I want to pick that up. And I put my hand where my eye thinks the shell is, and it's nowhere around. And I'm
I'm
like,
like, oh,
what? And I'm like trying to move around, like trying to figure it out. And it's like my eyes are not seeing where the reality is, right? Like the source of the light is not where I think it is. And it's because of refraction. Same thing, if you see your straw in water, if you have like a straw that's hanging halfway out of a glass of water, it looks like the straw is bent. You pick it up out of the water and now the straw is straight again. It's so fascinating. And you think it's just an optical illusion, like your eyes are playing tricks on you. And it's like, no, it's literally just the properties of light, right? It's not your brain, it's the light itself. And I love imagining, right? Imagining that you are a light ray and you are, let's say, coming in at a particular angle and you're going to strike water. Okay. What is going to happen? Well, we talked a lot about waves in a previous episode, right? And we talked about where waves travel the fastest of different kinds, right? We talk about how sound travels best when there is a medium. In fact, it needs a medium, right? But it travels better through a solid than a liquid than a gas because the particles are closer together because ultimately a sound wave is just vibrations that are transmitted within a medium, right, from one area to the next, right? It's a wave of energy, really, but carried through vibrations. Light waves really are the opposite, right?
mhm,
So we see the opposite trend. Light travels better in air than in water. So when you think of light coming from the air and going into the water, what we're going to see is its speed is going to change. Okay.
mhm,
And I always visualize this. I think maybe an even better one than I usually think is a shopping cart.
mhm,
If you
mhm,
are going in a particular direction and you're just moving, right, in a particular line, and one of the wheels of your shopping cart either gets stuck or hits the grass, right? Like what's going to happen? Let's say my front right wheel hits the grass. My whole cart is going to turn to the right,
mhm,
right? Because my left wheels are not slowing down. They're fine,
mhm,
right? My right wheel is slowing down. So I'm going to travel faster on my left wheel than my right, which is going to cause me to spin in a circle,
mhm,
right? The path that I was on was originally linear and now it has bent, right? That is exactly what refraction is.
mhm,
Um, I always will visualize it if I'm thinking like coming at an angle. I'll usually draw the waves themselves, and right as it's beginning to hit, if we're at an angle, part of that light wave is going to slow down while the rest of it, right, is still traveling through air. And again, it's showing that it's bending in a new direction.
mhm,
And that bending is really what's responsible for all the cool, weird properties that we've talked about so far. And it's also how your eyes work. It's also how,
mhm,
different optical images or optical instruments work. It's absolutely fascinating. And of
mhm,
course, like you said, the speed, which ultimately can lead to this bending, is really important between media. So when we talk about how light is going to bend and how to tell, we actually do have an equation for this, but we need to understand the differences in the properties of the two media. And we have
right, right.
numerical values for this.
There are some terms, some numerical values to know here. The first one, I think that's so critical, is what we call the index of refraction, right? Normally denoted as an n value. When you think about what the index of refraction actually is, a great way to think about it is how much does this medium slow down light? But it's kind of like a factor, like does it slow it down a lot? Well, that means there is a very high index of refraction. If it doesn't really impede the light a lot. Like the speed doesn't change that much. There must be a low index of refraction. And because, again, I love that example of the shopping cart, right? The more that it impacts the speed, the more that it will bend light, right?
Yeah.
The greater it is. So you can think of an index of refraction like how much does it slow down light? And therefore that will lead to the bending. And it's in recognizing that's what it is that's how you can get the equation for the index of refraction, where it's equal to the speed of light in a vacuum, which is c, 3 times 10 to the 8, divided by the new velocity of your light after it's entered this medium. So let's say our speed of light, goes down to 1.5 times 10 to the 8 meters per second. Well, then our index of refraction would be 2, right? Because it halved our speed of light, so therefore it's double. It's basically a factor. So that is this value. When you see that n value, that index of refraction, that's what's going on. And kind of building off that, once we understand the index of refraction, we kind of hinted to it, the greater that impacts the speed, the more it will bend light. And there's another kind of law equation that we need to recognize when we talk about that. And that's what we know as Snell's law, right? Snell's law, I always remembered it's Snell's law. It doesn't have anything to do with snails. I guess you could think about maybe the speed, right? Is a law that dictates by what degree, based on the change in index of refraction, by what degree will the angle change? Because with reflection, it was very easy. Angle of incidence equals angle of reflection. Very, very easy. However, now with Snell's law, they're not going to be the exact same, as long as the indexes are not the same. In Snell's law, the equation is the index of refraction of the original medium, so n₁, times sine of θ1, which is the angle of incidence, is equal to n₂, or the index of refraction of the new medium, times the sine of θ2, which is the angle of refraction, or the new angle, right? And so this equation is one that's very important to know, but it's one of those equations that while they can ask for it to solve in this equation, a lot of the times they're just asking for relationships here. It's not always like plug and chug, but rather if they say something along the lines of, well, if the index of refraction goes up, how does the angle of refraction change? Well, if you look at this equation, if n₂ increases, our new index of refraction increases, well, if it still has to be equal to n₁ sine θ1, well, then θ2 must decrease as a result. And so it's this relationship that's the really testable part of Snell's law, is recognizing how does the index of refraction change the angle of refraction, right? And that comes from Snell's law. Not to say that they don't ask you to solve ever, but that's what more of those questions will test on with Snell's law.
Yeah. And I think a good trend to just kind of keep in mind, and also one other thing that I wanted to mention with index of refraction, can you ever have an index of refraction of like 0.5?
0.5?
Is it
No, because you can't go
possible?
faster. You can't go faster
Can't go
than
faster than the
light.
speed of light.
Yeah.
Yes.
Yeah.
I've seen practice questions on that of which of the following is the index of refraction of this unknown liquid? And you see light is traveling from air into this unknown liquid or this solid or whatever, right? And always there's typically one option that's like 0.85, right? That can never be the case. If n equals the speed of light over the velocity in a medium, if the speed of light in a vacuum, right, which is 3 times 10 to the eighth meters per second, if that's the fastest we could go, how could that divided by the speed be less than 1? Okay, so just something to keep in mind. It's typically an easy kill if you are looking for an index of refraction. It should never be less than 1. Building off that, if you are going from a lower index of refraction medium into something that has a higher index of refraction, one of the trends that you can normally is that when you pass from that lower end medium into the higher end medium, you're going to bend what we say is towards the normal. Okay, so if you think of air or light from the air striking the surface of water, again, surface of water is flat, horizontal. The normal is perpendicular. Okay, so it's a vertical line. Whatever angle your light ray is coming in, as it passes into the water, it's going to get closer to that vertical perpendicular line. Okay, so it's moving towards the normal. If we were having, let's say you were snorkeling or whatever, you have some light source from the bottom, maybe like a pool light or something like that. If the light is originating in a medium with a really high index of refraction and coming out into the air, it's going to bend away from the normal. Okay, it's going to get essentially closer to the water surface from that vertical line.
Mhm.
So this is important to keep in mind, okay?
Mhm.
And I would understand that trend again. Mike, you put it perfectly with the mathematical way to verify. Don't memorize any of this. It's
Mhm.
very easy to lean into memorization with optics, but it's when you memorize, it's very easy to switch things up by
Mhm.
accident.
Mhm.
So the best way to do it is to derive it from your understanding of the equation, like Mike just did so well. But trend wise, keep that in mind. If you're increasing your n, you are moving towards the normal. Okay.
Mhm.
If you are decreasing your n, you're moving away from the normal. Um, and this actually brings in one of the really weird kind of
Mhm.
it feels like a combination of reflection and refraction. It's like really extreme refraction in a way.
Mhm.
Um, and it's this idea of what's called total internal reflection. Okay, now this is very specific. It can happen only when light is traveling from a medium with a very high or with a higher index of refraction into something that's lower, right? Now, when we are traveling to something with a smaller n, what we said is it's going to get farther from the normal. Okay, so again, if we think coming from the water, right, below a horizontal surface into air, right, there's going to be a point where at a given angle, you are shining light and okay, it's coming out, right? It's bending away from the normal, from that perpendicular. There's going to be a point though where you hit the surface of the water at such an angle that instead of actually coming out really close to the water surface, that light is actually just going to be parallel to the surface of the water. So a horizontal line. And then you don't actually see it, right? That light does not come out of the water, right? Because at exactly the perfect angle, it's going to be perfectly perpendicular, right? It's going to go like to the right or left on the surface of the water. It's not, that light is not coming out to reach your eye. If, and this is really cool, if you go past that critical angle, right,
Mhm.
you get closer to the surface, it's impossible to keep bending away from the normal, right? Like it's you can't do it anymore. And what we see is if you are past that critical angle, right, and you're going from, let's say, water into air, you're going to reach a point where no light comes out of the water. You're going to see all of that light just reflected right back down into the water. It doesn't leave. It's called total internal reflection. It's super cool. Um, it's very interesting to think about, I think, because that light is essentially trapped under the water because of the angle at which it was, being sent to, right, or
Mhm.
moving at the surface. Again, it's always from a high N medium to a lower N medium. And it's typically that incident angle is really big, right? The angle that's exactly that would make a angle from the normal of 90 degrees. So parallel with the surface. It's the critical angle.
Mhm.
This only happens past it. So
Yeah.
kind of cool.
Not just kind of very, very cool. Because when you think about like the applications, right? This is the reason why, like at a certain angle, like say you're going fishing. Like I myself, I wasn't always into fishing, but I've gone into fishing, which is a lot of fun. Like there are certain angles where there could be a fish there, like just beyond your sight,
Mhm.
like just at an angle. There could be right there, yet you do not see it at all.
Yeah.
And then once it comes a little bit closer, it just reveals itself. It's like it came out of nowhere. It's because before that point, the angle at which it would have come into your eye was so shallow that the light coming off of that fish could not escape the water and just bounced back in. Right? But once it crossed that critical angle, came a little bit closer to the normal, right? Then the light actually had enough of an angle to actually bend away from the enough or lessen the bend enough so that it could actually reach my eye. So this is the idea of total internal reflection where I kind of remember as like a fish can stay hidden. To help me remember, it only happens when you go from a higher end, so water is a higher end than air, rather than from a lower to higher. So like for context, some indexes of refraction you should know is the index of refraction of air, which is 1. The index of refraction of air is 1, and it is helpful to know the index of refraction of water, which is 1.3, right? The index of refraction of water is higher, so when light goes to water, it does slow down. But that's why when light goes from the air, like the light for me going into the water will never ever totally internal reflect. Whereas the light coming from the fish that's in the water up has the possibility to totally internal reflect. It won't always totally internal reflect. It depends on what's the angle there. But if it's at a big enough angle, far enough angle from the normal, it will totally internally reflect. So that's kind of, I use the fishing example to help you remember, wait, is it from high to low or low to high?
Yeah. Yeah, absolutely. It's cool. Again,
Mhm.
light is a fascinating phenomenon. Like
Mhm.
it really, really is. And these same principles that we're talking about with reflection and refraction really are the basis for everything else that we're going to talk about,
Mhm.
especially in this episode, but also it's critical. We're going to bring it up probably in future episodes as well. So we now have laid the groundwork. Okay, we've talked
Mhm.
about light behavior. Now we're ready to connect this to optics. Okay, and I'm sure some of you are like, sweet, lenses, mirrors. Yes, we got to talk about those things, especially because that's obviously very relevant to your eye, which, by the way, just because you were talking about it, one of the most common um, problems that you'll get, you might see air and water. You might see air and, let's say, like the surface of a puddle on the ground or something. But also, you do fairly often see light versus the index of refraction of your cornea in your eye,
Mhm.
for instance. Like there's a lot of really cool ways that you can see this applied. But ultimately, light is bending throughout the entire period that it's getting in your eye, especially by the lens of your eye, but even before it reaches the lens. Kind of cool. We'll talk about that later. Let's talk about optical instruments that are not our eyes. So lenses and mirrors. We've already talked about the basics of both of these. Basically, lenses are primarily refraction. Mirrors are primarily reflection. Okay, there are lots of different shapes of both of these, and there's different ways that those shapes create certain behaviors of light. Okay, but I feel like generally speaking, lenses, refraction, mirrors, reflection. Because a mirror is it's not meant to take some of its light or some of the light through it. Whereas, of course, if you think of like a contact lens or the lens in your eye, right, it's meant to transmit light
Mhm.
past itself. Um, so we should clarify shape and we should probably clarify behavior.
Yeah, yeah. I think shape is very interesting when it comes to optics because we've said kind of a term that, we've used quite a bit and we even referenced this before, which is mirrors, right? And when it comes to mirrors, normally when you and I think of a mirror, we're generally thinking of a flat mirror, like my bathroom mirror. However, when we talk about optical systems, the MCAT can't be so easy. And for a good reason. They have very important functions of curved mirrors, right?
Yeah.
And just like we have curved mirrors, we also have curved lenses. Now we have a name based on how it curves. This is what we describe the shape of a mirror or lens. And kind of my always rule of thumb, and I think the common rule of thumb is anything that caves in is has a concave shape. So we have concave mirrors, which again this reflective surface is caving in, and concave lenses, which that means they cave in. They get thinner as you get to the middle because they're caving in. Whereas I just remember that if it's not concave, it must be the other one, which is convex, right? If it's not caving in, that means it's pushing out, and that means it can't be concave, therefore it must be convex. And so these are the mirrors that are like curving outwards, or the lenses that are curving outwards. I think the most, salient example of a convex mirror is like one of those security mirrors. Those ones that curve out, you see them in like stores, you can see around the corner, right? That's a great example of a convex mirror because it's pushing out at you. Whereas like a concave mirror, I think examples like I think makeup mirrors are like usually concave mirrors. So those ones are caving in a little bit. And the strength of it will depend on that curvature, which we'll talk about in a little bit. But that's what we mean when we're describing the shape. When you hear these names, concave, convex, that's just telling you what's the shape of that mirror lens.
Yes.
Mhm.
And I think you bring up a good point of like, how curved is it? Right? Like,
Mhm.
how much is it going to impact the light that's coming out of it? Right. And you can imagine a makeup mirror typically is going to, when you're looking closely at it, it's magnifying everything. That's why it's helpful for individuals who want to put on makeup. It's like, oh, I could see every pore in my skin. Like, let me figure out how best to cover all this up or whatever, right? Or how to draw like, makeup art. Who cares? Right. Versus that the other mirror that you were talking about, the security mirror, right? The whole goal of that is to see more, to see a wider view than a concave mirror, right? And again, it comes down to the difference in point. Like I'm trying to see something very, very close. I don't need to see my whole face. I'm trying to zoom in on just a portion versus versus a security mirror. The whole point to have it around corners is to be able to see the entire area, right? So again, we could talk about these patterns in behavior as being really important. But when we talk about the degree of how curved it is, personally, I don't know about you, Mike, I always think of this as, we're talking about curves, right? We're talking about a curved mirror. I usually will imagine what is the circle that
Hmm.
completes this mirror?
Yeah,
So
100%.
like
Yeah.
if I see that this particular mirror is curved pretty extreme like a C, like a pretty strong curve. Okay, what could I draw on the other side that would make that a circle? Okay,
Hmm.
the radius of curvature is, if I made this a circle, what would the radius be of that circle? Okay,
Hmm.
like
Hmm.
that's essentially what we're looking at. And you can imagine a very high radius of curvature would be taking a particular piece of a huge circle. It's actually not that bent, right? It's
Hmm.
not that curved versus something with a really, really small radius of curvature would be a very tight circle. And therefore, that would be a pretty generous curve. Okay. And this is going to be related to our focal point, right?
Hmm.
Which, Mike, you put it really beautifully earlier. It's the point where, at least hypothetically, light will meet.
Hmm. Hmm. Yeah, no, I think when we talk about, and we kind of, when we brought up the mirrors, like the makeup mirrors, again, I don't use makeup mirrors that often, but for those who use makeup mirrors, they know there's different types of makeup mirrors, or some will like zoom in more than others, right? It's because based on how curved they are. Therefore, they will have a different radius of curvature because a lesser curve will be a bigger circle, larger radius of curvature. More extreme curve will be a smaller circle, therefore smaller radius of curvature. People have heard maybe this term of radius curvature, but they're thinking, okay, why is it relevant? Why am I taking the center of the circle? Because of that term you brought up just now, which is the focal point. Now, the focal point is this really important point of a mirror, and where that point will be is based on the radius of curvature, where the focal point or the focal length will always be half the radius of curvature. Right? Whatever the radius of curvature is, the focal point is between the radius of curvature and the mirror or lens we're talking about. Now, this point, like we said, right, is kind of the hypothetical point where light will meet. Specifically, any light that hits our mirror or lens perpendicularly to that mirror or lens, kind of horizontally to the mirror or lens, will reflect or refract to that focal point. So let's say I've got a concave mirror, right? Any light that hits that mirror horizontally will reflect through the focal point. Anyone who's studied focal point, I notice that it's a common kind of saying like, oh, all light passes through the focal point, and that is not correct. Not every single light ray will pass through the focal point. Only the light rays that hit our mirror horizontally or perpendicularly will pass through the focal point. This point is very important because now that we're talking about how this light bends, we might have multiple light rays that are hitting our mirror. And then how that mirror or lens bends it will determine whether those light rays come together or go apart. This is when we talk about the properties or the behavior that different mirrors or lenses portray, which is kind of like two types of behaviors: convergent behavior and divergent behavior. And kind of the name kind of tells you what's going on. Convergent behavior means those light rays are being bent towards one another. Divergent behavior means those light rays that they come in are diverging away from one another, right? And so it's very kind of important to recognize that yes, mirrors and lenses can do these things. When we talk about where those light rays are originating from, that's when we start talking about what the object is. Because we might be saying, okay, the light's being converged or diverged, but where did that light ray come from? So, for example, when you were looking at a mirror like this morning in the bathroom, you were the object, right? You yourself were the object because you were the source of the light, right? That is what we call the object. Another term that people I'll hear a lot of the times is what we call the image. Now, the image is where those reflected or refracted rays end up crossing, right? And that ends up, when you are looking in the bathroom mirror, that's what you see in the mirror. That is the image. And so a convergent mirror will bring in the light rays together that came from you to create a image. Well, a divergent mirror lens will take the light rays that came from you and diverge those light rays away from one another. But that's kind of interesting because when you're diverging, light rays, they don't seem to actually cross. So will we create an image? Well, we'll talk about that in a second. But I don't think there's anything I missed there when it came to convergent divergent behavior, Molly, was there?
No, I mean, we'll expand on it in
Yeah.
the next, few minutes, but I think that's perfect, right? We're just kind of getting our feet wet, like what's going on with this?
Mhm.
We're putting optical instruments into categories, right? Mirror
Mhm.
versus lens. Are we talking about reflection or refraction? If we are bending light, or if we're changing the direction of it in some way, is it going to focus on a particular point in a literal sense? Or is it going to scatter away? Like, okay, if my light rays are moving parallel to each other and now they're being scattered, they're not going to meet at a point, right? Like,
Mm.
what? They're just going to go away from each other. So, do they ever meet at a point? Like, not technically,
Mhm.
but if you follow all those lines back, what you're going to find is you're meeting at a focal point. So, or
A point.
a point, a virtual focal point, as you as you
Mhm.
implied earlier. And this brings up a really important set of terms that I think a lot of people get really confused about, which
Mhm.
is about images. Are they
Mhm.
real or are they virtual?
Mhm.
Okay, and I think it's important to again bring this back to mirrors. Okay, a mirror, a real image is going to be on the same side of the mirror as you are. A virtual image is behind the mirror, okay? Because you're expecting light to come off and be reflected and come back at you, right? When you think of a lens, lenses are meant to transmit light in vast majority of cases, right? So a real image is going to be on the other side as the object, right? Because it's meant to go through. That's the point, right? It might refract, it might bend, but it's not meant to reflect and come back, right? So we're bringing in images and we're talking about, real makes sense. Okay. Light is coming back at my eye from a mirror. That makes sense. It's striking my eye. Great. I got you. Right. Or it's going through a lens. Again, think of like, if you're wearing, I was going to say if you're wearing contacts, but actually we all have lenses, right? Like you're looking at a light source. Of course, you know that that light is coming through your lens and onto your retina so that you could see it, right? Like those make sense. A real image virtual breaks brains.
Mhm. Mhm.
Virtual breaks brains because it's like, well, how am I seeing something? How am I recognizing something if light is not actually meeting at any given point? Right?
Mhm.
Like, what does a virtual image look like for a lens? What does it look like for a mirror? How do we even perceive it at all?
Mhm.
And this is, I think, where it can be really fun to get out some lenses or some mirrors and actually play around with it. There are quite a few YouTube videos that will literally show how this works. I've seen one where an individual has a couple lenses and will actually just show how light can either be focused on a projector or it can't. No matter what you do with it, it's always out of focus. Have you seen these, Mike? I feel like
Yeah.
a visual makes it so clear. It's fun to
Right.
actually play around with it.
Right. Yeah. And that's always sometimes the limitations of like the medium that we're using now, which is just chatting. We don't a lot of times have the ability to show visuals because a lot of our listeners are like audio listeners. But I think a lot of times when you can experience it, like even in your day to day, you actually see a lot of real and virtual images, whether you know it or not.
Yeah.
Like real images, yeah, absolutely makes sense. Where you put it wonderfully, where okay, a real image for a mirror will show up on the same side as the object as you, and a real image for a lens will show up on the opposite side because the light is actually meeting. And that's how I always like to think of a real image, where the light is actually meeting. That's why it's real, right? Whereas a virtual image, the light's not actually meeting because, right, if we're diverting away, right, the light
Yeah.
doesn't, and that's generally for divergent systems, the light's diverting away, we can kind of pretend like they're meeting, right? A great example that you might see a virtual image, I always like going back to the security mirror, right? Because in a security mirror, when you look up at that mirror, what you actually see within the mirror are little people. You might see yourself in that mirror and you're seeing a little person in that mirror. However, you're not actually a little person in that mirror, right? The light's not actually converting there. And so that is a great example. When you see yourself, you're not actually seeing the light actually meeting because the light's spreading apart. You're just seeing where you think the light is meeting. It's kind of a weird thing to think about, but when you see the image within the mirror itself, that's how you know it's a virtual image. So a great example of that, when you look at the bathroom mirror. When you look at a bathroom mirror, you are seeing a virtual image. You are not actually in the mirror. That's not you, right?
What?
You are not. There's
Are you
not
sure?
actually, and it's kind of like funny when you see like little like babies like hit mirrors. Like they're like, oh, there should be somebody there. No, no, no. There's no one there, right? But that whenever you see the image within the mirror itself, that's how you know it's virtual. Whereas real images can be projected on a screen because the light's not actually, it's not like pretend in the mirror because it's not actually there. It's actually being projected or reflected or refracted onto something. You can see it on something else. So whenever it's in the mirror or really in the mirror or lens, that's how you know it's virtual. That's kind of always my kind of rule of thumb.
Yes. Oh,
Mhm,
for sure.
mhm,
And there are lots of patterns that we could talk about with converging and diverging systems and what kind of images they create.
mhm,
And this is where a lot of people memorize things.
mm.
And I really encourage you guys to actually get out a pen and paper and draw some ray diagrams, right? Like, oh, okay, given a convex mirror or a concave lens, what is light going to do when it strikes this mirror or lens? Where is it going to go? Is it going to diverge? Is it going to converge? How do I know, right?
Mhm.
There are also some pretty fun simulations that you could find on this online. I know PhET has an amazing simulation, PhET.
You think
So cool.
you think
So
maybe we
cool.
could
It's
drop
free.
the
You can
link,
mess around with
drop,
it.
you think we could drop it in the description to the
All
simulation?
I'll see. I think we can. I mean, it's
I
totally free online. You could also Google it, but I think we could maybe include the link.
maybe.
That's
If it's not a
that's my
link,
favorite.
it's
I
so much
found it
fun.
while I found it while teaching my fourth and fifth graders years ago, and I have never stopped. I teach all my adult MCAT students with the same thing. It's excellent to be able to visualize this, but I think it's important to understand the general trends. Okay.
Hmm.
And I think it's good to start with diverging lenses, or diverging systems. It should be
Hmm.
general, also true for mirrors, um, because the pattern there is the most clear, right?
Hmm.
A diverging system, as we've talked about, is scattering light. Light is
Hmm.
diverging after it interacts with this optical device of some kind, lens, mirror, right? The light rays are spreading apart. If they're spreading apart, how can we create a real image? Like they're spreading apart, they're never going to be focused on each other, right? Like that's not going to work, right? And so
Hmm.
what we're going to see is if you diverge, if you are a diverging lens or mirror, you are never going to create a real image.
Hmm.
You never will. It just, you can't. It's going to always be virtual. And in fact, it's actually an even more specific pattern. If you are a diverging lens, not only will you always be virtual, but you will also always be upright.
Hmm.
Okay. You will always have U and V together. No matter what kind of system you have, U and V together. If you are upright, you are also virtual. If you are virtual, you are also upright. Okay. UV, like UV rays from the sun, which is also light. Pair those two together. Okay. And on the flip side, if you are real, you are going to be inverted. Okay,
Hmm.
which is actually also a light term if you do IR, like IR spectra, infrared, that's
Oh.
also
Hmm.
light. Okay, so UV always together, IR always together. But diverging, if you are a diverging system, you are always upright, you are always virtual, and you are also always smaller.
Hmm.
Okay,
Hmm.
so smaller, upright, virtual, SUV for any diverging lens, it's very important. It doesn't
Hmm.
matter whether you're talking about a concave lens or a convex mirror, it's always that way.
It's
Okay.
always the case. Always, always. And whenever
Yeah.
there's an always situation, I think there's always a way to prove it. Because if it's
Yeah.
always, there's always a way to prove it. That there has to be a rule. And this is when we have to talk about some equations related to, lenses and mirrors, right? And there's kind of, I think, two main equations. There's a few ones, but there's kind of two main ones. The first one, which I'm sure maybe if we've studied this before, we've all seen, is what we call the thin lens equation, which is 1 over the object distance from the mirror lens plus 1 over the image distance from the mirror lens equals 1 over the focal length, which is the distance of the focal point to the mirror lens. This is our thin lens equation. We usually use this equation to solve for I, which is our image distance, this I value. And it's this I value that tells you a lot of information. Particularly, I think two pieces of information I tells you. One, whether it's real or virtual. If I is positive, it's real. If I is negative, it is virtual. That's the whole idea of I. But we said some terms before, things like inverted, right? Things like, oh, is it smaller or larger? But thin lens equation doesn't tell us any of that. All it told us was that the image was that was real and where how far it was from the mirror. In order to figure out whether it's inverted or upright or smaller or larger, we use our second really important equation, which is m, our magnification constant or value, equals negative image distance over object distance, negative I over O. It's this equation that will tell you whether it's inverted upright or smaller or larger. Particularly, you're going to solve for m, so it's whatever I was over O, right? And so if m is negative, that means your image will be inverted. If m is positive, it will be upright. That's what the sign tells you. And it is the magnitude of m that tells you whether it will be enlarged or smaller. Because like we said before, like take the makeup situation, for example. The image you created in that mirror was way larger, right? Because you need to see your pores. Whereas for the security mirror, if you looked at the images, they're actually way smaller. So it's the magnitude of m that tells you whether the image you see is bigger or smaller. And m that is greater than 1 will mean, oh, the image you see is much larger. Whereas an m magnitude-wise, I want to say this, magnitude-wise, less than 1 will mean that it is smaller, right? You'll notice if you actually look at these equations, a virtual image will be negative I. That means whenever you have a negative I, it will always be a positive m. Therefore, it will always be upright. And if you ever have a positive I, that means your m will always be negative, therefore it will always be inverted. So that's kind of like the why behind like the UV-IR. So UV-IR, I'm like, that's a great quick way. But if you ever like, you know what, Molly, I don't believe you. You can prove it for yourself using m equals
I I love that so much. Especially because with diverging situations, it's always SUV, right? Like
Mhm,
it is what it is. It's always if you have a diverging mirror or lens, it is SUV, smaller upright visual, call it a day. When we talk about converging,
mhm,
all bets are off. Okay, there
mhm,
are many different combinations that you can have. Okay, again, IR and UV will always be together. And you've
mhm,
proved it with the magnification formula. IR, UV always be together, but you can be larger and upright and virtual, like a
mhm,
LUV situation. You can also be larger and inverted and real,
mhm,
so LIR,
mhm,
and you could also be smaller and inverted and real.
mhm,
There are actually many different options depending on how far the object is from the mirror lens and also what the focal point of that mirror lens is. And it gets really confusing. And I myself, when I was studying optics, tried to memorize them all.
yeah.
Um, and I really got frustrated. I hated optics for a very long time because I would try and come from a pattern recognition place and try and like memorize the pattern instead of actually understanding it. And nowadays, I never do that. Like
Mhm,
I know diverging SUV, it can help very quickly evaluate, oh, if it's diverging, like I don't have to do any math. I don't have to pick up a pen. That's it. But ultimately, if it's not a diverging system, and even if it is, knowing why these
mhm,
patterns are what they are is infinitely safer for you on test
mhm.
day. Infinitely safer. And
Right.
plus, you can just use it. You can use this as a general frame of reference, right? You don't have to plug in a bunch of values. I love that you bring in all the equations because not only do we need to know them, but also we need to know how to use them and
Mhm,
why they underlie all the patterns of light behavior that we discuss. So I
mhm.
love that. Yeah, thin lens equation. That's honestly one of like, in my experience, one of the most used. It's not the most used for sure, but it's very
Very.
important. If you
If
have
there's
any
a
optical situation, you're going to use
It's
it.
using it. Yeah. Yeah.
Yeah.
And I like it because you can also, because we have all these rules, like, diverging, is always going to be, upright and virtual always. But you can actually, again, prove these rules using thin lens. Like, I challenge you to have a negative focal length, because that's what a diverging system will and have an image that's not negative. There will never be the case. Right? Try it out on your own. Go extreme. Try to disprove it,
Yeah.
right? Whereas for a converging system, there are many situations on a convergence. That means a positive focal length where you can have an eye that's positive or an eye that's negative. My always rule of thumb is that while converging system has all these different patterns, I always personally just always trust my thin lens equation. Like I don't
Yeah.
even think too hard about because like based on where the
Yep.
object is compared to the focal length to be like, oh, is it gonna be real? Is it gonna be virtual? I just trust my thin lens equation. I don't try to memorize it. Don't try to memorize it, please. Just trust your thin lens because the thin lens equation, as long as you use it correctly, will never, ever, ever steer you wrong. As long as you know,
Yeah.
it's just kind of hard because people don't like using it because it's like inverted. It's like 1 over O plus 1 over I. So make sure you know how to add and subtract fractions. Some good skills to work on. But if you know how to do that, then yeah, thin lens equation. Like every time you see a lens problem, mirror problem, you can expect to be using that equation.
Yes. Yeah. It's an MCAT point machine.
Oh my goodness, don't even get me started.
If you know that equation,
Oh my goodness, don't even get
you
me
will
started.
rack up the points.
Mhm.
I had to say it at least once. It's our like running joke
Oh.
of, oh, this topic is it an MCAT point machine or
Oh.
is it just content? Like a way to say high yield in our twisted MCAT obsessed brains. So, this material that we've covered so far in this episode, we've covered a lot, right? We
Mhm.
started off with a recap of light, just the general properties that we had discussed previously. We then talked about light behavior, reflection, refraction, what that even meant. We applied it to lenses and mirrors on a general sense, and then we really dove in with very specific information. We covered equations, we've covered constants. Okay, this is a good one to practice right
Mhm.
away because it's a lot of information and it's it's feels abstract until you put it into practice. Okay, so for all of our episodes, this holds true, but especially for this one, do not wait to practice this. Like, do practice problems, do flashcards today or tomorrow at the latest. Do not wait and do it next week. It's too late, right? You need to make sure that you apply this material quickly or else it will go away. I promise you.
Mhm.
Trust me, I've been there.
It will.
I've probably learned and relearned optics gosh, like 15 times in my life. You need to let that, neural pathway really sort of set down roots in your head, so to speak, with application quickly and immediately. And we have
Mhm.
practice questions on our website for this. You can use our QBank that's completely free, or any of our daily passages, or discrete sets, right? But get practice with this one way or another so that it doesn't disappear from your head.
Disappear, right? Some epic house forgetting curve stuff. And with that, by reviewing this, you'll be ready for our next topic because we've really talked about like the physics of light, how it behaves, how we have optics and lenses. But a great place, like we kind of alluded to, where there's a really important lens, is your own eye. And we'll be diving into the optical system, my goodness, and the lens in your eye and how that makes images in your eyeballs and how our brain translates that next episode. So get excited for the next episode. We're going to be really applying a lot of this stuff and bringing in some biological aspects, right? This is where the MCAT really loves to test this because it really combines biology and physics. So review this and then come back next episode where we're going to be talking about how it relates to the body. Until then, I hope you all have a fantastic rest of your day. Happy studying, and we'll catch you all in the next episode.
Bye, everyone.